Today we're going to talk about safety and efficiency in autonomous vehicles through planning with uncertainty, and how by planning better with better models and better algorithms, we can do better with respect to both of the goals of safety and efficiency. So here's just a map so that if you're going to fall asleep, you can know how much longer you have to hold that on. I'm going to start out with an introduction, then we're going to go to the first application that I studied, which is collision avoidance for unmanned aerial vehicles. Then we're going to go to an example with autonomous ground vehicles, autonomous cars, and how to do lane changing. And then we're going to talk about some of the algorithmic improvements we made for solving continuous Pom DPs. And then finally, I'll talk about how we're trying to share this ability to solve Pom DPs with more people through the PomDPs.jl software framework. So I'll start off with the introduction. So the basic premise of my work is that autonomous vehicle control is inherently a multi-objective problem. And two of the most important objectives are safety and efficiency. By safety, I mean minimizing the risk of harm to yourself and others. And then efficiency could mean a lot of different things. It could definitely mean efficiency with respect to fuel or something, or keeping the environment clean, things like that. But I think our most important resource right now is actually time. And so the main thing I'm investigating is how fast you can get from point A to point B. So let's look at the first requirement and how things have gone so far with respect to safety. So this is data from 2015, so it's a little dated, but it is kind of, we think that it's kind of representative for an autonomous vehicle program just getting started. So this shows the number of crashes and injuries per million miles. And the green bar is for autonomous vehicles. The blue bar is for self-driven or human-driven conventional vehicles. And these bounds are 95% confidence bounds. So as you can see, the best estimate is that there are actually more crashes per million miles than human vehicles. But we actually want that to be much, much lower here. We want it to be safe, safer than a human vehicle. So there's a lot of work being done right now on how do we accomplish that. So there is one way that you could be completely safe, guarantee with 100% certainty that you'd never, ever get in a crash. And that is to stay home, never go anywhere. But clearly this is not a good enough solution. The other extreme is just to throw safety to the wind and go for it. And you may think that that's kind of silly, like how could you ever prioritize efficiency over safety? But I think this is actually very important because the vehicle manufacturers are going to care a ton about it. Because if you're a buyer and you can choose between two cars and one car gets you to work faster, 5 minutes every day to work, then you're going to be very tempted to buy the faster, the more efficient car. So actually balancing these two extremes and being somewhere in the middle is extremely important. So there's several ways we could do that. One way would be there's several ways we can handle multiple objectives. One way is to constrain one objective and then optimize the other within those constraints. The other way is to scalarize them with a trade-off weight. And so since this is a multi-stage problem, at each time step we make a decision about what to do, where to turn, how fast to accelerate. Our total objective is, and there's also random uncertainty in how the other vehicles are and how the world evolves. Our objective is to maximize the expectation of the discounted rewards that we receive at all time in the future. So we have the state of the world at time t, the action that we take at time t, and we sum those up and multiply it by a discount factor gamma, which is usually 0.99 or 0.95. And that serves to keep this as a finite number instead of going to infinity if we didn't have that. So, but that doesn't tell us how to combine the safety and efficiency objectives. So the way we do that is by having a safety term, a reward as a function of safety that just depends on safety, and a reward that depends on efficiency, and then a weight lambda. So now we can think about what happens when we change this weight. So if we have safety on this axis and efficiency on this axis, then every control system that you create will correspond to some point on here. And better performance is up and to the left. So you want to have the best safety and the best efficiency. So if you create any control system, maybe you like write down a bunch of rules, it's going to lie at some point on here. But if you use an optimization algorithm and optimize this objective or the sum of this objective over time, then you can actually move along this, what's called a Pareto frontier. And if you have a large weight, you're going to prioritize safety, so you're going to be down at this end. But as you decrease the weight, you can move along this line and create different controllers by changing the optimization objective that lie along this line. Now, this is assuming a fixed model and a fixed optimization algorithm, a fixed optimization planning model and a fixed optimization algorithm. And choosing where we are at this point isn't actually really the job of an engineer. That's more the domain of a philosopher or a policymaker. And actually, if you go to Sarah Thornton's defense later this afternoon, you'll hear a little more about that. But what we can do as engineers is create better models of uncertainty, and better optimization algorithms so that we can actually move the entire Pareto frontier up. And so with a new model, M2, that's a better model of the real world, and a new algorithm, A2, we can have a control system that's provably better with any weight. So the main kind of freedom that we have in modeling that I'm going to talk about is uncertainty. And there are three types of uncertainty that I'll talk about. The first is outcome uncertainty. This is like flipping a coin, basically. So you know the distribution, but you can't do anything to influence how the coin lands. The second type is model uncertainty. So you can think of this as like a weighted die. So it also has random outcomes, but you don't know the distribution of those outcomes because you don't know the weight. But by observing the outcomes over time, you can learn more and more about the die, and then eventually do better guesses on how it's going to come out. And then finally, there's state uncertainty, which is sort of like the cards that someone else has in their hands. So that can change over time, and based on what that state is, you can play better if you have more knowledge about the state. So over time, you can learn about what the state of the other players' cards are and play better based on that knowledge. So in one sense, outcome uncertainty is kind of the easiest uncertainty to plan for, because with a coin, for example, you bet on either side, and it doesn't matter what your policy is, you're still going to get the same average reward. With state uncertainty, for example, it's harder to know how to play, but you have much more room to improve your strategy to do better. Another note is that model uncertainty can always be represented as state uncertainty. So you could include the center of mass of this die in the state of the world, in your representation of the state of the world, and that way you can represent model uncertainty as state uncertainty. So in a multi-step setting, this is kind of what that looks like. So the first model we have here is what's called a Markov model. And this is described by a state space and a transition probability distribution. So at each time, the system is in one of these three states, and then with a given probability, it transitions to another state. And the word Markov means that the probability distribution of the next state depends only on the current state and not on the previous history of what states you're in. So that's not very interesting because there's no decisions to make. We can study that, but we can't actually do anything to improve how it functions. When we have a Markov decision process, we add an action space. So these are actions that we can take to influence how the state changes. So for example, if we're in state 3 and we take action B, then we have a large chance to come back to state 3. Whereas if we take action A, then we definitely go to 1. So this action space allows us to maximize the reward function. Excuse me. So in real life, these states won't just be integers, they'll be actually the configuration of the world around you. So like where other cars are, where other vehicles are, where other people are, things like that. Now, the last problem that I'm going to talk about is the partially observable Markov decision process. And you have probably all heard this word at some point because we like to talk about it and sizzle a lot. In this model, you actually don't know the state of the world, which is when we're dealing with the world, when we're driving or doing really any task, we don't know the complete state of the world. I don't know if there's somebody out there walking by right now, for instance. So this is actually the best model of real life. So whereas MDPs and Markov processes only model outcome uncertainty, this models both state and outcome uncertainty. So instead of knowing which of the states you're in, you just have a belief about the probability that you're in a given state. Fortunately, we receive observations over time that are based probabilistically on the state according to this observation probability distribution. And so through those observations, we can learn more about the state and make better decisions. All right, so I'm going to outline my contributions real quick, just to so that you guys can be looking for them as I go through this. So the first is that we quantified the performance price of certifiability for UAV collision avoidance system and showed how to reduce it. Second, we quantified the safety and efficiency advantage of planning with internal states for an autonomous car. And third, I developed some online algorithms for Pom DPs with continuous state, action, and observation spaces, and showed that the current solvers are suboptimal, and we used weighted particle filtering to fix that problem. And then fourth, I led the development of the Pom DPs.jl software framework. All right, so now I'll move on to the UAV collision avoidance section. So this is a picture of the Google Wing delivery vehicle. So this is designed to deliver packages, and there's a bunch of advantages that you could get from this. You could get things that you need immediately, much quicker. You won't have to wait for a truck to get to you. You can just send things from point to point. The problem is there's a lot more consequences if these things run into each other potentially than with ground vehicles, because this could land on a house or land on a person or something. So we need to be very conscious of safety. And particularly, we need to make sure that these vehicles are not going to collide with one another or with manned aircraft. And one of the challenges is that we'll need to certify these control systems. And what I mean by that is proving that the control system will never command a sequence of events that will result in a near midair collision, given that the other vehicle does something. So simple deterministic algorithms are much easier to certify than more complex and probabilistic algorithms. So the kind of base algorithm that we looked at is very simple. I'm going to refer to it as the trusted resolution logic from now on. But what it does is it simply, our vehicle, which I call the own UAV, has a nominal path that it's trying to follow. There's an intruder, which could be human or another UAV. And we assume that it follows a straight path, and we choose the resolution angle that's closest to our original nominal path without ever passing within a distance d of the own UAV, or of the intruder. And this picture is actually simplified. This is throughout all time, it will never pass within a distance d. So the problem is there's a little bit of uncertainty in what the intruder is going to do. So one way to handle that, the kind of simplest way to handle that, is just by adding a little buffer zone to this, this avoidance region. So by changing the size of this buffer zone, we get a Pareto curve again. So the x-axis is the fraction of near midair collisions prevented, and the y-axis is the fraction without deviation. So this represents safety. Safety is better this way, and this represents efficiency, which is better in this direction. So if we start out with these two radii equal, we get this point here, which is less safe but more efficient. And as we increase it, as we would expect, it gets less safe, or more safe and less efficient. So that seems to work fine, but we want to see what the price of using this simple algorithm is versus something that's closer to optimal. So the way we do that is to formulate this problem as a Markov decision process. So the state consists of the ownership state, which is signified by this O here, and the intruder state, which is signified by this I. There's X, Y locations and the heading, and then a binary variable that says whether or not it's deviated from the course. The action space is the bank angle, and we have 5 choices for that. The reward function has efficiency terms, so a cost for every step, a reward in the goal, and a cost for deviating. And then safety terms, so whether a near midair collision occurs at that time step. And then the transition function is just Dubin's vehicle dynamics, so it turns along an arc based on either the bank angle or the intruder has random noise in it with a standard deviation, a Gaussian random noise with a standard deviation of 10 degrees per second. So to solve this MDP, we formulated as an MDP, how do we solve it? Well, here's an expanded version of the objective that I noted before. So our goal is to choose a policy pi. A policy maps every state to an action. And we want to maximize the value function. So the value function is the expected sum of future rewards, given that we start in state S and we follow the policy pi in the future. So in general, this is a hard problem because it involves all future time. So if we were to enumerate all the potential paths or action sequences that we could take, it would be too large to compute what we need to do. But fortunately, there was a guy named Richard Bellman in the 1950s who helped us a lot with this. And he introduced or helped codify the principle of optimality, which you can think of as every subpart of an optimal policy is also locally optimal. So if you think about plotting or finding the shortest distance between New York and San Francisco, for instance, if that happens to pass through Chicago, you also know that that route from Chicago to New York is also the optimal route from Chicago, an optimal route from Chicago to New York. So that's the principle of optimality. It seems kind of obvious, but it turns out to be really powerful. And it's expressed for MDPs in this equation, which is called the Bellman equation. I don't know if it's possible to love an equation, but I've had very strong feelings for this equation. As I'm sure many of you who are in this field have also had. This is actually for the optimal value function. This is true for the optimal value function, but it's also true that if you just apply this operator to the current estimate of the value function you have over and over again, it's a contraction. So that means it's guaranteed to converge to a fixed point or the fixed point of this value function, which is guaranteed to be the optimal value, which will allow us to find an optimal policy. And the great thing about this is it actually breaks it up into single step problems. So we have the state at t+1 and the state at time t. And this maximization, instead of being over all future time, is only over one step of the problem. So by solving this equation a bunch of times, we can tractably solve Markov decision processes. So what that looks like, the problem is it's only guaranteed to converge for finite state spaces. So if you have like integers as your states, but in all our vehicle problems, we're in continuous state spaces because vehicles can be anywhere. You know, it can be 1.7 meters away or 1.9 meters away, not just 1 or 2. So what we have to do is approximate this with a set of features. So we approximate the value function with beta, which is a set of features based on the state, multiplied by a set of weights, theta. And when we do the value iteration, we do the Bellman operation, and then we project this by solving a least squares optimization problem onto the subspace spanned by the linear subspace spanned by beta. So that yields, and this is what the features look like. So we have a couple grids. We have the intruder grid, which is based on 3 variables: the bearing to the other vehicle, the distance between the vehicles, and then the relative heading of the vehicles. And so if you plot that, it looks like this, with each one of those little arrows being a grid point. And then there's a similar grid around the goal with just the bearing and distance as variables. And we the actual feature values are the linear interpolation weights between these grid points. So if we run value iteration, that gives us a value function, a slice of which looks like this. The intruder vehicle is always at this point. Our vehicle is always pointed north, but each of the squares on this is the value function evaluated with our ship at that location. So as you can see, there's very high value near the goal, very low value when the intruder is about to hit us. So that induces this policy, which says in this red region, we should keep going straight. And in this green region, we should turn to the right as hard as we can. And this yellow region, we should turn to the left as hard as we can. So this, that actually has another Pareto curve. This gap between the Pareto curves could be viewed as the price of certifiability. So by using this simpler algorithm, we get this much performance difference. But the question is, can we do better than this without sacrificing the ease of certification? So the way we decided to do this was simply to prune the action space. So instead of just considering all 5 of these actions, we decided to only consider the actions that will result in a trajectory that never runs within distance d of the intruder. So this should be just as easy to certify as the other, the simple trusted resolution logic that I mentioned before. And if we do our value iteration with that problem, then we actually get this line, which is almost near the directly optimized MVP. So we can close this gap, this price of certifiability gap. All right, so that's the UAV stuff. Now I'll move on to the autonomous car stuff. So our kind of theory about how to make autonomous cars behave better is that we want to model the internal states. So if you just use the external states, which are the physical states that you can measure with sensors like position and velocity and turn signals, then you can't plan as well as if you reason about what's going on inside the other driver's head. So there's actually been quite a bit, or a fair amount of work on this by a lot of people at Stanford. They've demonstrated that qualitatively, this can produce some interesting and desirable behavior. What we wanted to do is quantify whether this is useful in a large number of simulations. So we can see that it does good things in single simulations, but we want to quantify whether it makes a difference in the aggregate. And you might think lane changing is a pretty easy task that's already solved by all these autonomous car companies, but this is actually from April 29th, so less than a month ago. This is in Phoenix, and we have an autonomous vehicle right here who's trying to get on the highway. And it actually is unable to find a gap or push its way into a gap. So it actually has to exit the highway here and go to try again another day. So this is something that, this is a problem that's still not completely solved. And my thinking on it is that modeling the internal states is going to be one of the keys to making this better. So in order to do this, we have to have a model of how other drivers behave. And we started off with the simplest model that we could come up with, which is IDM and mobile. So IDM is the intelligent driver model, which governs the longitudinal acceleration of the vehicle. And the mobile model is a lane changing model. So IDM is described by these two differential equations, which give the acceleration as a function of these parameters, which are interpretable. So it's like the desired speed, the desired time gap. So these parameter values are the internal states that we're considering for the other vehicles. And mobile also has a few parameters like the politeness, some braking and acceleration thresholds. So the problem that we specifically wanted to investigate is we have to change 3 lanes within 1,000 meters. So you have 1 kilometer to do 3 lane changes at normal highway speeds. And we formulated this as a Pom where the state is our physical state, the physical states of all the other cars on the road, and then the internal states of the other cars. Our observation is the complete physical state of the cars. So we know exactly where everyone is and how fast they're going, which is a little bit unrealistic because there's things like sensor occlusions. But we think that with standard filtering techniques, we can get a pretty good idea of what the physical state of the other vehicles is. And then our action space is the acceleration, or the longitudinal acceleration and the lateral speed. So we have 9 options with that, combinations of accelerating and decelerating. We also, well, I'll talk about the blue thing in a minute. So our reward function has, again, efficiency and then safety terms. So an unsafe action is defined as a hard brake, which is greater than 4 meters per second squared, which Uber considers a hard brake 6.5 meters per second squared. So we're a little slower than them, or we're a little more, I don't know. Our cars will be smoother if they use this. And then if somebody's going less than 15 meters per second, that's also an unsafe action. But we actually filter these actions just like we did with the planes, so that there are no crashes. No crashes occur in these simulations. So we say we consider each of these possible actions, and if it leads to a state where it's impossible to avoid a crash, then we prune that. But we always have this braking action available, which will ensure that there is always at least one action that our car can take. And this braking action is calculated online just to ensure that. All right, so to solve a Pom DP, a Pom DP is a little more complicated than an MVP, actually a lot more complicated. One of the key ideas is the idea of belief. So we can start out by defining the history, which is the set of all previous actions and observations. So this is everything you know about what's going on so far, all the observations that you've gotten about what's going on. And then the belief is a probability distribution over the state space. So this is the probability that the world is in all the possible states that you could consider, that encodes all the information that you've seen in the history. And you can update this as you go along using Bayes' rule, but it's computationally expensive. So another very important thing to recognize is that a Pom DP is a Markov decision process on the belief space. So a Pom DP is equivalent to solving an MDP, but the state space that you're operating on is the set of beliefs, which is a much larger space than in an MDP, an MDP on the same space in general. So there's 2 ways you could do this. You could do it offline, which is what we just talked about, where you calculate the value function before you ever get out in the real world, calculate the optimal policy for every state before you get out in the real world, or you can do it online. And the main idea behind this is the idea of constructing trees, where the root is the current state or belief that you're in, and each of these squares represents an action that you can take. And when you take an action, you transition into a new state. So we keep a value function estimate for each of these action nodes, and by doing that, we can choose the best action coming from the own current state. But one of the keys is that the online methods only calculate optimal actions for states that you might reach. So it's looking at a much smaller region of the state space than an offline technique. And that allows us to solve much larger problems like this one. The final kind of thing that we need to introduce before this is the idea of the QMDP approximation. So the Q value is similar to the V value function that I've been working with, except it also involves an action. So the Q value is the value function, given that you take action A on the first step. So this is like the value if you're in belief B and taking action A. So you want to maximize this to choose the best action. So the QMDP approximation is simply taking the Q value for the Pom DP with the belief is equal to the expected value of the expected Q value of the fully observable MDP times the belief that you're in that state. So this is like an expectation over the current belief, but it assumes, the key is that it assumes full observability after the next step. So it's like saying, I don't know the exact state of the world at this step, but immediately in the next step, I'm going to know it somehow magically. And this is an upper bound for the true optimal Q value for the Pom DP. So if we use the QMDP approximation, it actually makes us overconfident and gives us suboptimal plans. In particular, it won't take costly exploratory actions, and we'll see that a little bit later. So this is what it looks like in practice. There's a lot going on here, so I need to explain it. The green vehicle is the vehicle that we're controlling. These other vehicles are using the road, and the color represents how aggressive they are. So if they're red, that means they're really aggressive. If they're purple, that means they're pretty average. And then if they're blue, they're pretty timid. So there's this person up in the left lane being really timid and going really slow. I think there's like some technical terms maybe for what this guy is, but they're not really appropriate here. And then each of these little lines coming off of here represents our prediction of what they're going to do given that they're aggressive or timid. So for instance, since we're just starting off, we don't really have an idea about what the dispositions of these other drivers are. So we're predicting a lot of timid actions from this guy and a lot of aggressive actions. And then the white lines are our predictions of where we're going to go. So when it's calculating, or when it's actually running, it looks like this. It's calculating a new tree at every 3/4 of a second. So we were considering going up this way, but then we realized that that wasn't great. So we decided to go back this way. And as you can see now, after receiving some observations, we have a pretty focused belief about the behavior of these other guys. So all of our predictions about this guy are red, and all of our predictions about that guy were purple, that driver. We were actually able to make it over to the left lane within 1,000 meters with this planning algorithm. So if we look at this, we again have some curves here. The x-axis is again safety. This is how many of the episodes we were safe on. There were no unsafe actions. And then this is the fraction where we were successful in our lane change. So this is the first baseline that we could choose, which is where we assume that all drivers have the normal internal states. And so as you can see, that is can be pretty efficient. So we're achieving the lane change a large portion of the time, but it's not very safe. So on 3% of the episodes, we actually had unsafe things happen. The second baseline, which I think is the more interesting one, is where we model outcome uncertainty only. So in this, we don't try to estimate, or we don't try to estimate the state. We assume that the state uncertainty is all represented as outcome uncertainty. So this can be very safe. It can it can prevent 99% of unsafe actions, but it can only reach the goal a maximum of about 75% of the time. So this is too conservative. We also have an upper bound where there's omniscient, where we're omniscient to the internal states. So we know the exact values of the internal states. And this is a dotted line because we could never achieve this in practice. And then we have the first method that we use where we actually estimate the internal states. We use a particle filter to estimate the internal states and then just use the mean of those particle values to plan on. We can also use the MVP approximation, like I said, and that gives us this curve that's closer to the upper bound. And then finally, Pom CPA is another algorithm that takes more uncertainty into account. But in this case, it does about the same as QMVP. We can also, actually, I'm going to just skip this because we're running low on time. So now I'm going to talk about solving continuous POM-DPs and some of the algorithmic advances that we've made in this area. So I talked about this online tree that we're creating to make decisions. The most common way to construct this tree is through an algorithm called Monte Carlo tree search, which has 4 steps. First, we choose a path down this tree based on some exploration and value maximizing metric. Then when we get to a leaf node, we expand that, and then we run a rollout simulation with a heuristic rollout policy. And then we back propagate the results that we've seen up through the tree to build it so that we can get a value estimate at every action node on the tree. So this works for MDPs. Monte Carlo tree search was originally designed for MDPs. And you can apply that to POM-DPs by analyzing the MDP on the belief space. So that would look like this, where the orange kind of represents a belief of what state we're in. So we start off with this uniform belief. We take this action and we might transition to, depending on what observation we get, we might transition to this belief or this belief. So we could construct a tree like that, but like I said, the belief updates are extremely expensive. So about 2010, David Sunberg actually came up with an algorithm called Pom CPA, which uses state history simulations instead of belief updates, which is much more efficient. So instead of doing these belief updates, it actually just simulates some state trajectories through this, and then the belief is represented by these sets of unweighted particles that end up in each of these observation nodes. So that's Pom CPA. That's like an algorithm that's pretty widely used. But the problem is it won't actually converge to the optimal answer on continuous observation spaces. So to demonstrate that, we'll consider this toy problem, this toy Pom BP called the light-dark problem. And these are all the details, so I'm sure you can totally understand it immediately from those. No, actually, I'll point out some of the most important things. So the goal is to take action A equals 0 at state S equals 0. If you take 0 action at S equals 0, then you get 100 reward. If you take A0 at another state, you get minus 100 reward. So you better be pretty sure that you're at 0 before you take action A. Otherwise, you're going to get a big negative reward. And then there's a -1 reward for every step. In this light region, you get very accurate observations of where you are. And in the dark region, you get very noisy observations. The state is represented by this y-axis, and the x-axis is the time step. So the optimal policy looks something like this, where we actually go to the light region, we get a bunch of good observations, and then we know exactly where we are, and then we can go down to the goal region and take action A equals 0 with confidence. But let's see what Pom CPA does. So since the observation space is continuous, every time it creates a new branch here, it generates a new observation, which makes it a very shallow tree and very wide. And so that actually makes it so it tries to go for the goal as quick as possible, but it's never confident enough to take that action A equals 0 and get the reward. So this is clearly not very good. So some other researchers presented some necessary conditions for consistency for these algorithms on continuous spaces. And the first two are that an infinite number of child nodes must be visited, and each node must be visited an infinite number of times. So that is not happening here because each of these nodes is only visited once. But what we can do is do a technique called double progressive widening, where we limit the number of children to k into the alpha, where k and alpha are tuning parameters, and n is the number of times the parent has been visited. So instead of generating a new node on every time, this gradually widens it. By limiting how many children you have, it causes you to visit previously generated children over again. So this actually meets these two necessary conditions. So we can apply this in an algorithm called Pom CPA with double progressive widening. Now, unfortunately, you'll see that that does something similar to this. And the reason is because it only actually ever inserts one state into each of these observation nodes. And we can actually prove that a modified version of this algorithm converges to the QMVP approximation. So the reason for that is what I'll explain here. We start out with our Pom CPA tree. Then we first make the observation that since the observation is continuous, each of the observations that we generate is unique with probability 1. And that means, so we're inserting unweighted particles into these nodes, so we can only insert them if the action and observation history up to that point matches exactly. But since our observations that we generate are unique with probability 1, it means that only one state particle will ever end up in each of these beliefs. So really, that belief node or that observation node is only an alias for that state. So that makes this actually behave as if it's a Monte Carlo tree search tree on the fully observable MDP, except at the root node. So this is just, it functions exactly as if it was solving the fully observable MDP, except at the root node where there is a belief that it's generating these things from. So that's exactly the QMVP approximation right there. And so we can say that it converges to QMDP, and we'll show that with experimental results. So Pom CPA DPW, as we said, is suboptimal. And we can add a third necessary condition for consistency, which is that an infinite number of particles must be added to each belief node, given that we do an infinite number of iterations of this algorithm. And the way to do that is to, instead of inserting unweighted particles where the history has to match exactly, we use the observation probability distribution to insert weighted particles, like a standard sampling, a standard particle filter. And that will fulfill that necessary condition. So then we get this algorithm called Pom CPA, which instead of these unweighted particles has these weighted particles which better represent the belief. And we can see that that actually goes to a pretty good policy where it goes to the light region, localizes, and then goes to the goal and gets its big reward. So we tested this on a lot of other problems. The first one is a benchmark from the other literature. And we compare it, so we have this new algorithm, Pom CPA, then we have particle filter trees with double progressive widening, which we were also the first ones to use. This is that we know of in the literature. This is where you, instead of inserting particles at each iteration, you run the entire particle filter at every time. So this is basically just constructing the belief tree, but with a particle filter with a fixed number of particles approximation. This QMDP is the exact QMDP solution, which we can calculate because this is a discrete problem. Pom CP with DPW is the other algorithm that we talked about. And then DESPA is another, probably the leading online PomDP algorithm at this point, which was which is from some researchers in Singapore. And then these two algorithms are applied to a discretized observation space. So this one, since it's already discretized, this would be the same as this for this one, but anyways, DESPA actually outperforms all the others because this is one of the problems that was that DESPA was designed to solve. So it performs the best on this, but you can see that these other algorithms perform about the same. Now, when we go to this problem, which is the one I just described to you, you can see that all three of these algorithms perform the same. So just like we predicted, Pom CP with DPW and DESPA are unable to outperform QMDP. But since the observation space is a single dimension, it's super easy to discretize. So actually, discretizing the observation space with Pom CP and DESPA actually performs a little better than Pom CPA and PFT here. But if we make the observation space higher dimensional, so this is the problem, I call it Subhunt, where we're a submarine, we're trying to hunt down another submarine, and we can choose whether to take an active sonar ping, which will decrease our probability of killing if we engage, or a passive, maybe these are unmanned submarines, so we don't have to do any killing. So, so we can either take an active sonar ping, which will give us better information, but it'll also give up our position, or we can do a passive sonar listening, which gives us worse information. As you can see, now discretization doesn't work either. So all of the previous algorithms perform the same as QMDP, and the only algorithms able to outperform it are Pom CPA and PFT. So this one has a discrete state and action space as well. We also wanted to test this with continuous state and action spaces and a continuous observation space. So in this problem, the target follows the van der Pol oscillations, or the van der Pol differential equations, and we're trying to get it, we're trying to tag it, but there's also these barriers that we can't go around. So in this one, Pom CPA outperforms slightly all of the other algorithms. And then finally, on the problem that I just showed you, the lane changing problem, since there's little information gathering, DESPA actually does the best. Little costly information gathering, I should say. Like when you, just by going along on the road, you gather enough information to do the things that you need to do. So DESPA actually wins pretty handily. But this, we wanted to demonstrate that for more realistic problems, PFT actually performs significantly worse than Pom CPA. So that's why Pom CPA we think is good. So with all of these up here, you can see that Pom CPA actually only performs the best on one of these problems, but it's among the top 3 in all of the problems. So we think that it's a good general purpose algorithm. All right, so the last thing that I'm going to talk about, we're over time, is PomVPs.jl, which is our software framework to share the joy of solving PomVPs with the world. So what it is it's a way to bring together 3 different people. The person who writes a PomVP problem, the person who writes a PomVP solver, and the person who runs a PomVP experiment. Oftentimes, 2 of these people are the same people, but we want to be able to connect them. And so we have a list of functions that provide an interface for them to all communicate consistently. There's a couple of challenges with this. One is that PomVPs are computationally very difficult, so we need to have a very fast framework. And Julia provides this. It's nearly as fast as C in many cases, most cases. And so that provides the solution to that. The other problem is that there is a huge variety of PomVPs and solvers that we might face. And I won't go through all of these, but I'll just highlight one kind of difference that there could be. So you may want to specify your problem in an explicit way where you explicitly outline the probability distribution. So that would look like this for a discrete problem, or like this with the probability density function for a continuous problem. And some solvers need that information to work. So you have to specify that for some solvers. But in many cases, it's very hard to specify the probability distributions, and instead what you have is a black box generative model. So you put in a state and action, and you get out a new state, action, and reward. But we want to combine these into one framework. So there have been other attempts, or I guess other software packages that have done a pretty good job, especially of solving the first problem. So the most recent one is APPL, Approximate PomVP Planning Toolkit, which has the despot algorithm and the SARSUP and the MCVI algorithms, which is great in terms of speed. But they say on their website, at the moment, these 3 packages are independent, but maybe one day they will be merged into a single coherent framework. So I'm here to tell you that that day is today. We have PomVPs.jl now. So the way we solve specifically that explicit versus generative problem is we actually have 2 interfaces. We have the explicit interface and the generative interface. But if you define your problem with the explicit interface, you automatically get the functions from the generative interface implemented for you. So that allows you, if you define an explicit problem, you can use all the solvers like SARSUP, which uses the explicit interface, or you can also use these solvers that just use the generative interface. Whereas if you have a more complex problem like freeway driving, you just have to implement the generative interface, and then you can use the solvers that are designed to work with that. We've also connected through a package that Jayesh wrote to some deepRL solvers with deepRL.jl, and then we think it will be easy to add a factored representation of problems for specific domains where factorization matters a lot. And then just to illustrate how this is making the world better for programmers, I have this algorithm is the despot algorithm written out in pseudocode. And this is the old C++ implementation. So it's got a lot of functions, a lot of variables are hard to map between these. And then the PomVPs.jl implementation looks like this. So we got 3 functions right here. They're named prune, explore, build despot. The variable names are the same, and you can easily map between them. So it's a lot easier for people to read a paper, look at your implementation, and see that it works. And this also runs almost as fast as the C++ code. So we think this is going to allow a lot more people to do research and be educated about PomVPs. So here are the conclusions now. First, we showed that solving UAV collision avoidance problems with an MVP offline offers safety and efficiency improvements, and we can do that while still incorporating conservative constraints that are easier to certify. Second, in a simplified highway lane changing scenario, there's a significant performance gap caused by ignoring the internal states. If you ignore the internal states, you'll plan worse. But fortunately, this gap can largely be closed using PomVP planning. Fourth, the current online PomDP solvers are unable to solve PomDPs with continuous observation spaces that require costly exploration actions. Fifth, these new algorithms, Pom CPA and Ph.D. DPW, are the first algorithms to obtain better than QMDP performance on some of these problems. And then sixth, this PomDPs.jl interface provides a fast and easy-to-use framework for PomDP research and education. I've tried to integrate with the community by doing publishing in peer-reviewed conferences and journals, and these 4 specific contributions are in these 4 papers right here. This is all during my time in grad school, not just here at Stanford. And then here are the future work items that all of you can go out and now solve. So first, I think it would be good to investigate the effects of communication in lane changes. So we didn't actually even have turn signals in the work that I did. So that makes it, that's like one of the most unrealistic things about those simulations. So I think we should add that kind of stuff. And there has been some work, particularly in Marco's lab, in doing some of this. Second, we need to test PomDP lane change planners on driver models learned from real data instead of this IDM and mobile models. And then third, we need to apply it to simpler situations and then test it on real vehicles to see if it actually works. Fourth, in the algorithmic domain, I really want to extend DESPA to handle continuous PomDPs, or I think there's other people who have actually thought about that as well, because it's actually able to plan much deeper. It has, the way that it does the planning allows it to build deeper trees and actually have better worst case performance than the MCTS-based ones that we've been using. Second, I was pretty frustrated by not being able to find good theoretical guarantees about the convergence of algorithms that I proposed, so I would like to pursue that or work with someone to pursue that in the future. And then we also need to thoroughly investigate parallelism. I've thrown some stuff together to check whether it can be parallelized, and it can, but I think a thorough investigation of that would be extremely useful, because to deploy these algorithms in the real world, although they were running on real time in these simulations, parallelism would allow us to do much better planning. Seventh, for PomDPs.jl, it would be awesome to have declarative interfaces. So right now, to define the simplest problems, you still have to write a new class and write some functions for that. But it would be cool if we could just declare the state space is this, the action space is this, and have that generate all the code for you. And then 8, generating factored interfaces to allow, if you have some structure in the problem that you can exploit, we want to add that.